OChemStars, this is Mrs. Vanderlei bringing you the very first OChemStar video for this year. So we are going to start from the beginning, and we need to review certain topics from what you should have learned in your previous chemistry class, okay? No, we aren't going to do the whole thing. I just hit some highlights, and really this all goes around with when you talked about the covalent compounds and that whole chapter. And so we started talking about Lewis diagrams, and then we went on and talked about polarity, and you may have heard about intermolecular forces and VSEPR, and we're going to hit all that again because that's what we need to know about organic chemistry. So lucky, if you like math, well, maybe organic isn't for you, but there really isn't any need for math in this class. A little bit later on in this unit, we're going to subtract two numbers, two electronegativity values. That's going to be the most math you're going to get. So anyway, we're going to start from the beginning. We're going to review what you should have learned about Lewis dot diagrams. So if you would, can you get out your periodic table that you're going to need to work on this, okay? So if you need to pause this and get your periodic table, go for it, okay? And then come right back. Okie dokies, I hope you have your periodic table now. So it says draw the Lewis diagram for each element listed, okay? So what is it that we need to determine the Lewis diagram for each element? All right, well, we need to know their valence electron. So let's look. So here's my periodic table. I just found this off of the internet. That was really pretty because it has colors, And I'm looking at the groups, and we learned last year, whenever we took chemistry, that group 1 has a valence of electrons of 1, and group 2 has valence electrons 2. And what does valence mean again? It means outermost, okay? So if you get the potassium, remember we had the 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. That's your potassium. So do I really care about all those inner electrons? Are they involved in bonding? The answer is no. So I'm only interested in the valence electrons, all right, the outermost electrons. So this would be your 4s1. Well, as it turns out, if you looked at the trend, every single one in the first group has one valence electron. All of them in the second group has two valence electrons, just like what I wrote up here. See that? All your transitions, and if you really care, all your lanthanide and actinides all have a valence of 2. There's a couple of exceptions, but we're not going to worry about those. You remember why? Because if I looked at scandium, okay, right here, so it was 4s2. Do you remember what came next? It was what? 3d1. Well, which is outermost, 4s2 or 3d anything, okay? It's your 4s2. So your valence electrons are your 4s's, all right, or your 5s's or your 6s's. So all of these in group 3 through 12 is a valence of 2. And once we get back on boron or group 13, we pick up again, because if you recall, we have 2s2, 2p1, so the 2 still are your outermost. So this has 3, 4, 5, 6, 7, 8. So your noble gases, and this is important, have 8. That's your octet, except for helium, which only has 2. And that is also important because of hydrogen, okay? So keep this in mind, all right, as we answer the question. Let's go back to our notes. So how many valence electrons did hydrogen have? 1. All right, so how do I do that? I put a dot there. What do you think? Okay. What's next? Well, carbon. Go back. How many valence electrons did carbon have? Carbon had 4. All right, so it has 4. So if it has 4, that's a 4 right there. All right, how do I do 4 dots? Do you remember how I do this? I go 1, just make like a square, 2, 3, and 4. So carbon has 4 bonding sites. Look at that. So nitrogen has 5. You can go back and check that for yourself. So you remember how we do this? We just kind of go around a circle. Well, actually a square. 2, 3, 4, 5. Oxygen has 6. So remember we do this? 1, 2, 3, 4, 5, 6. Now what does that mean? These are my lone pairs. I'm not going to bond here, okay? Here are my singleton electrons. This is where bonding is going to occur, okay? Chlorine has 7. So we do around the circle again, square again, I guess, and here and here and here. And what does that mean? How many places does chlorine have to bond? It only has one. And then finally, neon has 8. All right, and again, I think you'll get the idea that you're going to fill this up. And I'm not going around the circle. I just think it's a little neater if I do it this way. And what does that mean? Is there any bonding sites for neon? Not at all. All right, that's why it's a noble gas. That's why it doesn't bond. All right, now that's all well and good, but that's not really what's going to help us in organic chemistry, is it? All right, so what's going to help us in organic chemistry is that we're going to make Lewis dot diagrams for compounds, and more specifically, covalent compounds. All right, and so these are the rules that I like to use, and I'm going to be consistent when I use these. Now, it depends on what teacher you may have had in your first year chemistry class. The rules may be a tad different, but you should still end up at the same place, okay? So this is the rules that I like, all right? So number 1 rule, and you'll see I do this every time. Calculate the sum. That means you're going to add of all those valence electrons. That's why you have your periodic table of the atoms in the formula. And it says choose the central atom. In organic chemistry, it is always carbon, okay? Arrange all the other atoms around carbon. If there are more than one carbon or another central atom, arrange them in a line first, okay? Then insert the pair of electrons or dashes between all the elements that are bonded together. So the carbon or whatever your central atom is and anything else that goes around it, okay? Now what? It says, this is important, place the electron or the remaining electrons around the non-central atom so that the octet is achieved on all the non-hydrogen elements. Leave the central atom to last. Number 6, this is where you need to do a little bit of math, okay? Determine how many electrons are still remaining. Use these to make lone pairs until all the valence electrons are used. If no electrons remain and the octet is not achieved, then you have to consider double or triple bonds will be needed. Now, this is important. Carbon and nitrogen can have single, double, or triple bonds. Oxygen can only have single or double bonds. And there's going to be one major exception to this, and it's carbon monoxide, all right? So if I look at carbon monoxide, it breaks several of the rules, all right? And in my knowledge, now I don't know every organic compound out there, all right? But in my knowledge, that is the one exception to several rules. Carbon monoxide would have a lone pair on the carbon, only one I know of, and it will have a triple bond on the oxygen, only one I know of, all right? So when we talk about organic chemistry, carbon monoxide is not an organic compound. Remember what we said our definition was. It is a hydrocarbon in its derivatives. There's no hydrocarbon for this to be a derivative of, okay? So keep that in mind. So let's go ahead and do some practice examples, okay? Okie dokie, so what's rule number 1? Rule number 1 is to add the sum of all your valence electrons. All right, so how many valence electrons does carbon have? 4. How many does each hydrogen have? 1. Well, how many do I have then? Well, look at this. I have 1 carbon at 4 and 4 hydrogens at 1. 4 plus 4 make 8. So I have 8 electrons to play with, all right? So choose my central atom. It's going to be carbon. All right, now I have 4 hydrogens around it. So I'm going to use dashes because it's a lot easier to do that on the computer. All right, so there's that, and then there's another dash, and then here's another dash. So go ahead and count these. How many have I used up? 2, 4, 6, 8. Hey, folks, that's how many I have. I'm done. Do I have to worry about, what does it say here, lone pairs? All right, so insert pairs of electrons or dashes between, and they're bound together. I did that. Place remaining electrons around the non-central atom. There are no remaining electrons, all right? So I don't have to do that. So then I don't have to worry about number 6 either, okay? So let's look at the next one. It may be a little bit different. So let's try the next one. Add these up. How many does nitrogen have? Well, look on your periodic table. How many valence electrons does nitrogen have? 5, all right, and then I have 3 hydrogens at 1 each. You're going to get to know that pretty well. It adds up to 8 again. Okay, so what's my first row? What's my central atom? It's not carbon. I don't have carbon. Here's a huge clue. You might want to write this down. Hydrogen will never, ever, 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 ever be a central atom. And why not? It can only have one bond. Okay, so if it's not hydrogen, it's going to be nitrogen. So I can put nitrogen here in the middle. Okay, so now what? I'm going to put the 3 hydrogens around it. Okay, 1, 2, and then 3. And then how many electrons have I used? 2, 4, 6. Well, folks, how many do I need to use? I need 8. So what do I do with the remaining 2? What does it say? Place the remaining electrons around the non-central atom. Well, I don't have to worry about that, okay? Leave the central atom to last, okay? It's a hydrogen, so I don't have to worry about that. So how many electrons are still remaining? 2. Use these to make the lone pair until all the valence electrons are used, okay? So I'm going to make these a lone pair. And how many electrons have I now used? 2, 4, 6, 8. That's what I need. I'm done. Okay. Why don't you try the next 2? So pause this, do it, and when you're done, come back. All right, welcome back. Hopefully you paused it and worked on it. So I added up all my electrons. I have 2 hydrogens at 1 each. I have 1 oxygen with 6, adds it up. All right, so here's my central atom. Remember, hydrogen can't be central, never, ever, ever. And then I'm gonna put 2 hydrogens around it. All right, and how many how many electrons have I now used? I've used 2, 4. How many do I have left? I have 8. I'm not going to put any more around hydrogen, can't do that. So that rule up there didn't apply. So now it says, put the remaining electrons around your central atom as lone pairs. All right, I'm going to do that. So I've now used up 6 electrons, 2, 4, 6, and now I'm going to put another lone pair there, and there's 8. All right, and there we go. So hydrogen HF actually is a hydrofluoric acid. If it's in the aqueous state there, has 8 electrons again. There seems to be a trend there. All right, so here's my central atom. I'm going to put the 1 hydrogen here. And now what? All right, how many electrons have I used? 2. How many are left? 6 more. So I'm going to put 3 lone pairs around the fluorine, and there you go. Okay, so check out these next couple. All right, here is SF2. All right, let me get situated. All right, so how many valence electrons do I have over here? Well, I think I have 20. Holy cow. I have 1 sulfur with 6. I have 2 fluorines with 7. So 6 plus 14 make 20. Okay, so same rules apply. Okay, so here's my central atom. And then I'm going to put my 2 fluorines. Oops, sorry about that. 2 fluorines around there. Okay. Oh, sorry, I blew it. There we go. All right, so I'm going to put a fluorine here and a fluorine here. Okay, so now what? Watch, I have to apply that rule that I skipped a couple times. Okay, it says place remaining electrons around the non-central atom so the act is achieved on the non-hydrogen elements. Leave the central for last. All right, I do not have hydrogen here. So what does that mean? I need to put dots around the fluorine. So I need to have the octet on the fluorine. So there is 8 around fluorine, 8 around fluorine. And now how many have I used? Ready? 2, 4, 6, 8, 10, 12, 14, 16. How many do I have total? 20. Where did my other 4 go? On my central atom as lone pairs. So there it is. Okay. Why don't you take a moment out and do the final 3 here and see how you do. Okie dokies. Hopefully you paused it and you came back. All right. And folks, I probably should have prefaced this earlier. When I say pause this and work on it your own, I want you to do that. I think you're going to get a lot more out of it if you try it first and then we go over it. Then you just watch me do it, okay? Oops, I should plug in my thing. I'm going to pause this so I can plug in my cord. Hang on. Welcome back. I'm plugged in now, okay? So I went ahead and, oh, I was going to tell you that when I'm telling you to pause this and do it, you should really pause it and do it, okay? Just saying that. So here we go. We have 5 electrons for phosphorus. 3 times 7, remember fluorine has 7, that's 21, that's 26 electrons, right? So here we go. Here's phosphorus. And I'm going to put my fluorines around the phosphorus. I only got 3 of them, okay? Believe it or not, phosphorus can have more than 3. All right, and then what? All right, what did the rule say? Of your non-central atoms, make sure they achieve the octet as long as they're not hydrogen. So I need to put dots around the fluorine. All right, and when you're done with this, if you count, there are 24 electrons. All right, 24 electrons. What does that mean? I need 2 more left. What am I going to do with it? Make them a lone pair. All right, let's try another one. You notice I have hydrogen again, so the rules are going to be a tad different. Here I have the hydrogens. Oops, I need another hydrogen here. There we go. And now what? Do I need to add anything around hydrogen? No. Hydrogen only gets 2, just like helium, all right? So 2, 4. Quit there. Don't put anything else around hydrogen. So I need 4 more electrons. I can certainly do that. I can make 2 lone pairs on the sulfur. There I go. All right. And then finally, the sulfur tetrafluoride. I have 32 electrons. Here we go. Here's I said sulfur, silicon tetrafluoride. And I'm going to put my 4 fluorines around here. There we go. And now what? Well, once I get done here, there we go. Now what? I'm going to have to use that rule where I'm going to put electrons around the fluorine. All right, it has to achieve the octet. All your non-central atoms must achieve the octet, except for, as you know, the hydrogens. Give me a few more seconds here. And then start counting while I'm finishing up. How many electrons have I used? Well, there's 8 and 8 and 8 and 8. 8 times 4 is 32. Do you put anything else around silicon? No, you don't. Okay, so let's go ahead and let's see what the next page is. Okay, so the rules are going to be the same, at least to start off with, all right? And you're going to see we're going to have a little issue here, okay? So the first thing I'm going to do is figure out how many electrons I get to play with, and I get 12, okay? Well, there is not really a central atom. I have 2 identical oxygens, all right? So pick one, all right? I'm going to pick the left one. I'm going to make sure it fulfills the octet. Okay, so how many have I used? 2, 4, 6, 8. How many do I have left? 4. All right. 1, 2, 3, 4. Now what? Does each oxygen have 8 electrons around it? Let's see here. 2, 4, 6, 8. That one does. 2, 4, 6. That one does not. So what did we say we needed to do? Let's go back and look at the rules. Look at number 6. Determine how many electrons are stereomanding. Use these to make lone pairs till all the valence electrons are used. I did that. If no electrons remain and the octet is what? Not achieved, then the double or triple bonds are going to be needed. Okay, let's check this out. So double or triple bonds may be needed. Here we go. So what am I going to do? I'm going to take my eraser and I'm going to erase 2 electrons. And where am I going to put those 2 electrons? Meet me in the middle. All right, so what has now happened? How many electrons does the left-hand oxygen have? 2, 4, 6, 8. How many does the right hand have? 2, 4, 6, 8. We're done. Okay, so you end up with a double bond. So if I were to do this again, all right, it would look something like this. All right, and then you have, 2 sets of lone pairs on each. Now, purely habit, why did I make them any like that? Well, that's kind of foreshadowing of our VSEPR, where you're trying to get those electrons as far away as you can from each other. Wait a minute. That sounds something like social distancing. Maybe VSEPR was the original social distancing. That's pretty clever. I'm gonna have to write that one down. All right. Sorry. So now what? Let's go ahead and do N2. Okay. Here's my I only get 10 electrons, so I'm going to start off here. And last time I made my left hand oxygen, let's make my right hand. Let's put all electrons around my right hand nitrogen. You ready? So right hand nitrogen, 2, 4, 6, 8. I only got 2 left. All right, there we go. Ruh-roh! My right-hand nitrogen is hunky-dory here. My left-hand nitrogen only has 4 electrons. So my left-hand nitrogen has not achieved the octet, right? So what I say, I had to erase, and what happens, all right? I'm going to make a double bond, okay? So now what? My right-hand nitrogen has 2, 4, 6, 8. That didn't change. My left-hand oxygen has 2, 4, 6. Aw, nuts. All right, so now we need to erase 2 more because that didn't work. Double didn't work. So now I need to do this. And now I have 2, 4, 6, 8 around the left, 2, 4, 6, 8 around the right. We are done. That's a triple bond. So if you want to do this again, so, well, that's not very neat, isn't it? All right, sorry. So there is my triple bond, and I'm going to put my lone pair like this, right? Again, I am foreshadowing. Why did I put them on the ends and not on top or bottom? Because I want those electrons to be as far away as possible. Now, again, I just created something kind of clever there. It's social distancing, isn't it, from the other electrons, okay? So I'm going to make them as far away as they can, so I put them on the ends. All right, let's keep going. Let's look at the next. So here's carbon dioxide and the dinitrogen tetrahydride. There's another name for it, but let's not worry about it. And anyway, so why don't you go ahead and figure out the Lewis structure for both of these, okay? And follow those rules like I showed you. So pause this for real. When you're done, come back. All right, welcome back. All right, so here is carbon dioxide. I'm looking at 16. So I'm going to do this and here and here. And then I'm going to start putting my dots around everything. Okay, so I'm going to go like that. And then I'm going to go around like that. And guess what? Each oxygen is fine. Okay, 8 around that oxygen, 8 around that oxygen, but guess what? Ruh-roh, carbon only had 4, so we need to put a double bond here. And then what? Well, I'm not done yet because carbon now has only 6. I'm going to do this, and we're going to put another double bond here. So you're going to have carbon with 2 double bonds with the oxygen, okay? Now, what did you notice about the next one, all right? You got 10 electrons, it looks like. Nope, wrong one. You have 14 electrons. I just kind of showed you one coming up. And so I have 2 central atoms, don't I? I have 2 nitrogens. I'm going to do that. Now I have 4 hydrogens. Now, why did I put 2 on each nitrogen? Why didn't I put 3 on one nitrogen and 1 hydrogen on the other one? Let me just kind of say this. We're going to see this quite a bit. Nature prefers symmetry. All right, so if you have a choice between 3 and 1 or 2 and 2, pick 2 and 2. All right, and so now what? I've used 2, 4, 6, 8, 10. All right, I still have 4 more to go. And there you go. Wow. Do you need to make double or triple bonds? It's a nitrogen after all, and the answer is no, you don't. Make sure you count your electrons. In this case, I threw in a tricky one, or I don't know if it's tricky or not, but I threw one in where if you did it right, you don't need to make double or triple bonds, do you? Okay, it worked out great the first time. All right, go ahead and do C2H4 and C2H2. All right, if you did it right, you would have done something like this. You have a double bond between the 2 carbons. And the next one, if you did it right, you'd have a triple bond between the 2 carbons, okay? Now, what's going on with the next set? It says, draw the Lewis structure for the non-binary, which means what? More than 1 central atom. And again, these are typically organic. So what's been my first step each time, all right? My first step has been add up your valence electrons. Okay, let's do that. All right, and then go ahead and pause this And go ahead and do these two for me, okay? I want to help you with the next two, so don't really go ahead. I want to talk about them before you do them, but I think you can do these two right now, okay? So see what you can do. Come back when you're done. Well, isn't that interesting? You both have 14 electrons, a little bit different, all right? So there's the first one. I have the carbon and nitrogen are your two central atoms, the hydrogens are around it, and nitrogen ends up needing one lone pair. It's the same thing with over here, and as it turned out, oxygen needs two lone pair. Why did I put any lone pairs in the carbon? Because folks, carbon already has 4 bonds. You're not going to put any extra lone pairs on it. It only, it only can take 4 bonds, period, 4 what we call electron groups, okay? You're not going to add more lone pairs on carbon. All right, so I want to do something real quick with you. Let's look down at these next two examples, all right? And I've already gone ahead, I've already gone ahead and figured out how many total electrons these two need. But look how this is written. And this is what I want to tell you first. If you ever see the C double bond O, or excuse me, COOH or COOC or COO something, all right, you're going to have a double bond oxygen on the carbon and then a single bond. So let me kind of show you what the skeleton of the first one would look like. So if you ever see OO like that, you're going to do this, all right? You're going to put a double bond O off of one and then a single bond O off the other. So then what's next? Okay, I got to put some hydrogens in there. So on this first carbon, here we go. How many hydrogens do I put on there? I put 3 on there. All right, so 1, 2, and then 3, okay? How many hydrogens are on the next carbon? None. Why not? Because carbon already has the octet. Carbon already has 4 bonds. 2, 4, 6, 8. Don't put anything else on that carbon, all right? And then what? Is there anything else off of that O? Nope. All right. Here's this O. Is there anything off of that? Yeah, you have a hydrogen. So now I have 24 electrons. Let's see how I'm doing. 2, 4, 6, 8, 10, 12, 14, 16. Huh. How many more electrons do I have? 8 more. How many lone pair is that? That's 4 lone pair. Well, I can't put any on the carbon. There's no room to put any on the carbon. I'm going to put them on the oxygen. And notice what happens when I put them on the oxygen. Now, does each oxygen achieve the octet? The answer is yes, it does. All right, so there is that organic compound. And that's a very important one, actually. It's acetic acid. That's vinegar, by the way. And look where I had to put the extra electrons. Okay, so why don't you go ahead and do this one, which, by the way, is an ester, and see how you do. Okay, so pause this, come back. And there you go. All right. So if you actually want to name that correctly, there'll be methyl ethanoate. It's an ester. We'll talk about that later. Okay. So anyway, that is how you would do Lewis structures. I'm going to stop here. I think that's plenty for you to do. And so you go ahead and then do the ed puzzle that will follow. So don't wait to be great. We'll see you next time. Bye-bye.